Hello everyone, and welcome to the Stat Online lecture for this week for Chapter 6. So I'll be showing you the notes and the examples right here, and I also want to make you aware of a new web resource I've added. So if you go to your Blackboard page, so yours doesn't quite look like this, so I can give you the student view. So your web page, when you go inside Stat, will look like this. And if you look at the content area, I have added a new content piece called Normal Distribution Calculator. So we'll be doing some normal distributions. And what you can do is you can click that, and you will get a nice calculator that we will be utilizing in this lecture. And you can also use, rather than having to have a graphing calculator, and your Blackboard page is still open. So I've got it set to open in a new tab. So when I start using the normal distribution calculator, just go ahead and click that, and you can do your homework problems in the exact same way. Okay, so let's get started with Chapter 6. So the first section is 6.1, and that is continuous probability distribution and the normal probability distribution. So section 6.1, continuous distribution, and also the normal probability distribution. Okay, so let's have a look at what those things are and why they're important. Mostly we'll be looking at normal distributions this chapter, but continuous distribution is a little more general notion. So kind of the idea of a continuous probability distribution. It's just that we have a discrete random, so a continuous random variable, so it models a continuous random variable rather than a discrete random variable, as some of our other previous models have done. So remember, a continuous random variable means that it can take any value on an interval of values. So it could be any possible thing, whereas discrete was basically just like counting numbers usually. And normally what's going to happen is we're going to have something like an x-axis, and then our distribution will have some shape. Maybe it's skewed one way. And the area underneath this whole curve is equal to 1. So we can think of areas between 2 points as actual probabilities that they're going to occur. So if we had some x equals a value and some x equals b value, then we could calculate the probability that our discrete random variable is between a and b by actually calculating the area between these 2 points. So this shaded area right here would represent the probability that the continuous random variable is between those two x values. So right now it's kind of not so obvious how we would do something like that, because we don't have a standard way of finding these values. So that's kind of where the normal distribution comes in. So the normal probability distribution is a specific case of one of these, and it's really the most important one. We'll see in the next chapter that whenever we take sampling distributions, that the distribution that we create out of even a possibly non-normal distribution will behave normally. So what this is this is a bell-shaped curve that is going to be symmetric. So that should be curve. And it's going to be a probability distribution, so the total area beneath the curve is 1. The curve is symmetric about the mean. And the last point is the two tails of the curve extend indefinitely. So they're basically asymptotic with respect to the x-axis. So the picture roughly looks like we have some picture like this. It's supposed to be perfectly symmetrical. So we get something like this. These two curves keep going on and they approach the x-axis. And if you could somehow do the whole area, it would exactly equal 1. And it's perfectly symmetric about the population mean mu. So the entire shaded area, if you could shade the whole thing. So shaded area equals 1. Okay, so since the mean is in the middle, if you would do each part, you get 1/2 to the left and 1/2 to the right, which is very nice. Okay, so one of the things that we're going to be using is what are called z-scores, so or z-values, let's say. So what is a z-value? A z-value or z-score is a unit marked on the horizontal axis of the normal distribution. And denoted by z. Okay, so this is kind of where the calculator is going to come in. So what we'd like to do is describe some, so that middle part is just going to be for the mean, I guess, and say we have our distribution. It looks like this. The z-score is going to tell you how many standard deviations you are away from the mean. So kind of if we think about mu as being centered at 0, we can think of 1 as being 1 standard deviation to the right, 2 as being 2 standard deviations to the right, 3 as being 3 standard deviations, and then we can do it this way too. This is actually going to be what's called the standard normal distribution. So each of these would be z-scores. So if I looked at z equals 1, I could actually compute a probability. So I could do the probability, I could think about it two ways. I could think of the probability that the values are actually greater than 1. So let's look at our calculator and see how they denote that. If we go back to the normal distribution calculator, notice they have p of capital Z is less than or equal to z. So if we go back to the notebook, if we had something like capital Z is less than or equal to our value 1, then what would the picture look like if I just do a little miniature version of the picture? I'd be looking at the 1, and I'd be shading all the values to the left. What is that going to actually be? Well, so here, just let it be known that the mu is equal to 0, the mean is equal to 0, which is the median because it's symmetrical, and the standard deviation in this example is equal to 1. So when we go to our calculator, the way we want to figure this out is we have the mean is equal to 0. We have the standard deviation is equal to 1. Did I get that backwards? Nope, mean 0, standard deviation 1, just like we had there. And then we want to calculate the probability that the values are less than 1 to shade that part. Excuse me, the probability is what we want to know, so we put in the standard z-score. So basically, you're always going to know on this calculator the mean and standard deviation, and you're going to want to figure out one of the other ones, so you're going to leave it blank. So when we click calculate, it'll fill in the other box, 0.84134. So we can come back to the notebook, and we know that this probability is actually going to be 0.84134. So that describes the probability that our values are actually less than 1. So if we would take this and shade it, that shaded region would be 0.84134 out of the entire region. Quickly, what if we wanted to do the probability in that same scenario that z was greater than 1? So we had our little 1 here, and let's say we wanted to calculate the probability that z is greater than or equal to 1. Well, we would be shading not to the left now, we'd be shading to the right. The thing we want to use is we want to use the fact that the area of the whole curve equals 1. Because our calculator, if we go back to the calculator, notice it always only specifies the cumulative probability for the values less than or equal to the z-score that you give. It doesn't give the ones greater than. So sometimes we'll have to do some basic symmetry arguments. So to do the probability that z is greater than or equal to 1, what we'll be doing is really the probability that capital Z is less than or, we'll be doing the probability of the whole area minus the part that we know. So this will really be 1 minus the probability of z less than or equal to 1, which we just figured out. So this would be 1 minus 0.84134. And then we might use a regular calculator to figure that out. 1 minus 0.84134. And that gives 0.15866. So that would be our answer. And if we think about this in terms of the picture, what are we doing? We're doing the picture that we want to know. This picture is really equal to the area of the whole curve minus the area of the curve we figured out in the other part. Okay, so if we have this area and we take away that area, we're left with the area that we want to know. So maybe we'll do another interesting one. So what if we have, let's say we have a normal distribution with, let's say, mu equal to 0 and standard deviation, in this case, equal to 3, and we want to find the probability that, I don't know, let's say negative 1.5 is less than or equal to x is less than or equal to, we'll say, 2. Well, what does this picture look like? With these normal distributions, I find it tremendously helpful to draw pictures. So again, we have the normal distribution centered at 0. And now the standard deviations jump by 3s, so they'd be 3, 6, and then you'd have most of your observations minus 3, minus 6. So we've got negative 1.5 right here, and then we've got 2 right here, And basically we're trying to find this probability. But with our calculator, we can only find probabilities from all the way from negative infinity up to a point. So what are we going to do? Here's the idea. We're going to do the probability up to 2. And we're going to take away the probability that was up to 1.5, minus 1.5. So basically, the picture right here, this picture, is the same as if we do the picture up to 2 and then take away the part from 1.5. That's all that'll be left is the picture that we started with. Okay, so we can figure out each one of these things out with that calculator. So let's go ahead and approximate those values. So let's go back to Blackboard in the StatTrack calculator. So in our example, the mean was 0, but the standard deviation was not 1. Remember, the standard deviation was 3. That's going to make a big difference. Okay, the first thing we want to do is we want to figure out the values where the z-score is less than 2. So we enter 2 and then we calculate, and we get 0.74751. So let's come back to our notebook and write that down. So the values that are less than 2 are 74751, and the values that are less than negative 1.5, we go back to the calculator and we do that. And we get rid of that, and we go ahead and we get 0.30854. And then that's going to be our answer when we subtract those two. So the probability that negative 1.5 is between x is between 2 is given by that value, 0.74751 minus 0.30854. So this is 0.43897. And that would be our probability. And that's all there is to it when we're doing our basic normal distribution calculations. So on the homework, maybe I'll pull that up, the Chapter 6 homework, just so we can take a look. If we go to Blackboard, and then let's say Wiley Plus, and we look at the assignments, then I'm sorry, I forgot to switch out of student view. So let's go back. Let's go to Wiley Plus. Yeah, that's where we want to be. Assignments. Let's look at some of the Chapter 6 questions to start off, and we'll get a feel for which one of these are actually going to have these type of questions. Oh, Chapter 5. I meant to do Chapter 6. We're in Chapter 6. So notice the first one says something like, find the area of the standard normal curve between z equals 0 and z equals 2.2. When they say standard normal curve, that's all they mean is mu equals 0 and sigma equals 1. When we come down to the next one, is this the one that's assigned? I just want to make sure I'm doing the one that's actually assigned. I believe I assigned something slightly different. Yeah, okay. I think we have a few more problems than that. Yeah. I'll give you, so this first one says if x is a continuous random variable, what's the probability that x assumes a single value? Let's think about that real quick. So far on all these things, we've been looking at areas. So that first question they look at on the homework describes something like this, right? So we have, say we have a standard normal distribution like this, and we're thinking that the probability is just a single value. So say this value, x equals a. Well, so what is the probability? That x equals a. Well, for continuous random variables, probabilities are given by intervals. That correspond to areas on our distribution. So in this instance, if we look back at our picture, the probability that you have a single value, that is an area that has a length that might have some value, but the width is actually equal to 0. So the area equals 0. So the probability would actually be 0 in this case. For a continuous random variable to have a whole interval of values, you would actually have to have it have some substantial width so you could actually get an area. Okay, so you really need two values, like a to b, and then be able to calculate that. All right, let's go back. Okay, so that's what happens for a single value. I noticed that when I was looking at the homework problems, I couldn't do it without actually previewing the answer. So I'm just going to kind of let you know that the first few questions, we're going to be doing these sorts of areas arguments with the normal distribution. And if you have any problems, just let me know. They're basically the same thing. We're always going to be able to figure out a certain area from the left up to any value. And then what we're going to do is just use that calculator. But let's think about how these things work again. So so on that previous one where I had the x, that really should have been a z. So let's just notice here we have x values. Like we could have the mean being, say, 20, and then let's say the standard deviations are so the z-score, what it's really doing is it's specify the number of standard deviations you really are. So let's say we have a normal curve with mean equal to 20, and let's say the standard deviations are let's say 100. And say this, so this is our curve. Looks something like that. So if you have 120, what would its z-score be? It would be actually equal to 1, because that's one standard deviation above. Say you had negative 80. What would that be? That would be 100 away from 20 to the left, so that z-score would be negative 1. So really what's going on is we have x values specified by mu and sigma, and the z-score determines the number of standard deviations. We are separated by. Okay, so basically 20 would be mu, 120 would be mu plus 1 sigma. If we would go up to 220, that would be adding another 100, so this would be mu plus 2 sigma. Similarly, negative 80 would be mu minus 1 sigma. If we would go down to minus 180, that would be mu minus 2 sigma. So just always keep that in mind when they're asking for a z-score or something like that. We could also go the other way with these normal distributions. For example, let's say we knew an area let's say we knew an area and a value. So let's say this has the mean, I don't know, let's just say 25. So we have a normal distribution with mu equal to 25. And let's say the standard deviations, I don't know, let's say they count by 50s. So sigma here is equal to 50. And then let's say we want to know for what z-score is the probability of capital Z less than or equal to lowercase z equal to, let's say, 83%. So basically there's some value up here, probably around here, and this whole area is equal to 83%. Or 0.83. So we basically want to know, this is some z-score. Z equals what? Okay, well, we can do that on the calculator as well. We can go back to StatTrak. And what do we know this time? Well, we knew that our mean was 25. Our standard deviation was 50. And we know that we want to know when the probability is 83%. And we don't know the z-score. So we can go ahead and calculate. So in this case, the normal random variable will have value 72.7. Oh, that's actually giving the normal random variable. We wanted the z-score. Where was the normal distribution calculator? So this is normal. So this is the one in terms of the z-score. So notice there's also one in terms of the normal distribution value. But let's do this again. So our mean was 25. Our standard deviation was 50. And we want to know when what the z-score is when the cumulative probability is less than or equal to 83%. So we calculate, and again we get 72.708. Okay, so that is giving the value. So it's saying this value right here is 72.708. So that's what the x value is. So the x value is occurring, actually I was a little bit off, it should have been here. So the picture is basically, we know the picture, I'm going to draw a new one just so we know, is right here at 72.708. So that's the x value, where we get the shaded area being 83%. But notice that's the value of the continuous random variable. That's not actually the value of the z-score. To figure out the value of the z-score, I'm actually jumping ahead a little bit to next section, but this is called standardizing a normal distribution. So the z-score tells how many standard deviations away we are. So how are we going to do that? Well, what is our mean? Our mean is at 25. So what we do to get the z-score is we do 72.708. We figure out how far it is away from the mean, 25, and then we divide by the number of standard deviations it is. And that'll tell me the z-score. So let's go ahead and do that. 72.708 minus 25 equals this, and then we divide by 50, and we see that it's 0.95. 416 standard deviations above the mean. Okay, so that's how we figure out the normal curve, the z-score of a value. So that's something we should note. So when we have a normal curve, whose mean is different from 0, or the standard deviation is different from 1, we need to standardize an x value to get a z-score. So the way you go about doing this is the z-score is always given by x minus mu over sigma. So this is the formula. So given an x value, we use the formula above. To find the z-score. So let's do a few examples of these. Okay, so you will get some very simple examples of this on the homework, just calculating a z-score. So for example, given a normal distribution with, let's just say mu equals 10 and sigma equals 8, find the z-score that corresponds to x equals 14. Really easy, we just do z equals 14 minus 10 over 8. So we just end up with 6 over 8, or 0.75. So there will be ones just like that on the homework. Not too much to think about. Okay, so that's really it for 6.1 and 6.2. So the next thing to look at is 6.3, applications of the normal distribution, which are really just story problems. So we won't be doing anything new there. We'll just look at a couple examples. So 6.3, applications of normal distribution. And these are basically just word problems. Okay, so let's just look at some examples. I'm just going to go into the book and go over a few ones that come to mind, because really there's no new techniques here. We just use our calculator, and then we make sure we do the symmetry arguments. And if you get stuck, send me an email and I will certainly be able to help you out. I know this is a little bit confusing at first, but the techniques are actually pretty straightforward. So this one says let x denote the time taken to run a race. Suppose x is normally distributed with a mean of 190 minutes and standard deviation of 21 minutes. if a runner is selected at random, what is the probability that A finishes in less than 160 minutes and B in 215 to 245 minutes. Okay, so this is pretty much the same stuff as before, nothing too complicated. We've just actually got some context. So we have a normal distribution of runners in this race, and first thing we want to identify is the mu value, the mean, that is given by 190 minutes, and the standard deviation is given by 21 minutes. So part A, we just want to figure out what is the probability that the runner, so we have 190, what is the probability that they finish in less than 160 minutes? So this is 160, we're looking for this part. So basically we're looking for the fast runners, because half of them finish slower than 190. Well, this is pretty easy, so the probability that x is less than or equal to 160 minutes, we just go back to our trusty calculator, and we have the normal random variable. We know that the mean was 190 minutes. We know the standard deviation was 21 minutes, and we want to figure out the probability that x was less than 160. So we can go ahead and just click calculate, and I typed the x value into the probability. Okay, let's go back. Sometimes I get confused on where this goes exactly. Let me click on normal. Okay, so we're going to change the mean to 190. We're going to change the standard deviation to 21, and we want the probability that he finishes in fewer than 160 minutes. Does it work this way? See, it has z less than or equal to z, so we might need to standardize and get that z score. Let me just click this. I'm pretty sure we need to standardize, but I want to double check because I'm not so sure. All right, cool. So yeah, we do need to standardize this. So let's go back. Okay, so for this one, we have the area, and this is exactly what we want to figure out. So basically first, figure out z-score of 160, then use calculator. Okay, so our z-score, we do 160. Yeah, because we do x minus mu over sigma. So then we take away the mean over 190, minus 190, over the standard deviation 21. So this will be a negative z-score, which makes sense because it's left of the mean, negative 30 over 21. So let's type that into the calculator, see if we get something to plug in. So 30 over 21, I know it's going to be negative, I'm just going to remember. So that value, let's plug it in. So we want the z-score, we'll type in, I'm going to use like 6 decimal places, 1.428571, 1.428571, and we go ahead and click calculate. That's the probability. All right, so let's start over with the normal. I'm going to copy and paste this. Sorry, I'm not proficient at using this calculator yet. Okay, normal. So the z-score, so we want the z-score is this. And we're trying to get the probability that z is less than or equal to our z-score. Our mean is 190, and our standard deviation is 21. So finally got it typed in right. There we go, 0.00003. See, the normal random variable it's giving is 106, though, which is not what we want. Oh, I forgot to do it negative. Can't get this right at all. All right, so let's go back to normal. We're at the normal. So we have 190. Gosh, sorry about this. 21, and then our z-score was negative 1.41. 1.428571. Then we click calculate, and we should get the probability. Gosh. Okay, so when it's on the z-score, we should be getting that. But our normal random variable is not 106. Why this is funny. So let's go back. Sorry. 160. So we want to know when the cumulative probability is less than 160. Right, and this is the right value. This is 0.07656. So you really got to pay attention to whether you have the normal random variable or the other one. Okay, so let's go back to the notebook. So the probability is that value we got right there, about 7%, 0.07. 656. Or we would say there is a 7.656% chance that a runner finishes in less than 160 minutes. All right. Now we want to do part B. So remember, what was part B asking? So in 215 to 245 minutes. So this is another one of those ones where basically we need to figure out the two pictures, and then once we figure out the two pictures, we're going to have to subtract them. So, right, let's think about our two pictures. We have the picture, so remember the mean was at 190. We have 245 somewhere over here. So we want to use our calculators to figure out the 245 picture. Then we want to do the other picture where we have 190 and then 215. So this picture is a smaller area, and then we'll get our answer, which is 215 to 220, which is basically some sliver to the right of the mean right there. Okay, so let's figure out both of these on the calculator. Let's see if we can do it a little bit better this time. I know we struggled last time, or I struggled. So now we have the normal random variable. So those are the x values. If it ever has the other value z, it wants the z values. So first we're doing 245. We want to find the normal variables less than 245. Same mean and standard deviation. All right, so that's 99.559. Okay, so let's go back here. So this is 0.99 559. Then let's figure out the other one. So we want to find the values less than 215. Calculate that. 0.88307. and this will give us the probability that we desire. So I just want to do it in my calculator so we don't make any more silly errors. So 0.99559 minus 0.88307. This will give us 0.11252. Okay, so the probability basically that 215 is less than or equal to x is less than or equal to 245 is 0.11252, or in sentence form, the probability that a runner finishes between 215 minutes and 245 minutes is about 11.252%. Okay, so let's end there. There will be applications like that. If you look through the book, they also explain how to do this stuff with a table, and I've kind of steered clear of the table. We have the calculator. You can do these calculations by hand using integrals, so the old tables basically made these values very quick, and I know we've gone through the actual probability calculations in a lot of the other distributions. If you're really interested, though, the function, so I kept drawing that picture where we have some normal distribution, where this is mu, and we have some sigma value. Is actually the equation of this, if we call it f, is given by f of x equals 1 over sigma to the square root of 2 pi with e raised to the negative 1/2 divided by x minus mu over sigma squared. So it's a very complicated formula, so we're just going to stay away from it and use the calculator and kind of stay away from the table too, but I just want you to be able, because the calculator is a good resource, so we might as well use it. We just need to be aware of the symmetry arguments we need to make. Also, another thing, but this is something we dealt with before, so in terms of the shape of the normal curve, this is true for most distributions because sigma represents the spread. If you have something like this, flatter means it's more spread out, so sigma is bigger. And kind of like steeper. So a bigger hill in the middle, sigma is smaller because the values are more bunched together. So that's the big dichotomy if you're ever trying to think about sigma and the actual shape of the normal curve. A lot of times we'll deal with a standard normal, which just means standardizing the x values to z-scores, and then basically we've translated one normal curve back into the standard normal curve. I may say a few more things about 6.4 and 5, but I will do that in a previous lecture. I've kind of gone on long enough now, and this will be enough to get you started. So good luck on the homework, and email me if you have any questions. All right, thanks. Bye.